All right, let's dive into one of the most fundamental shifts in modern AI. But here's the thing, this isn't a story about more processing power or bigger data sets. Not at all. It's about the death of a very old, very stubborn problem in computing, the problem of waiting.
Take a look at this sentence. Simple, right? You and I can read it and get it instantly. But for a machine, this simple string of words, well, it hides a serious bottleneck, a problem that for years really limited how well we could process language at all.
So, what is that problem? What's going on here? It really comes down to dependency. To figure out that the word ran refers to the cat and not the dog, a system has to understand the relationships between all these words. But how can it possibly do that if it's forced to read them one at a time in a strict line? And that gets us right to the core issue. We're going to call it the problem of waiting. You see, for certain systems, there's this strict, unbreakable rule. You cannot process word number 5 until you are completely, totally finished with word number 4. This creates a kind of forced sequential patience, which, as you can imagine, becomes a massive computational traffic jam.
To really see this in action, let's look at how older systems would try to tackle our sentence. We'll call this first approach System A, or, maybe more fittingly, the dependency chain. So System A chews through text step by step in this really rigid sequence. First, it processes the. Then, and only then, can it move to cat, which has to literally wait for the to finish. Next up is that, which, you guessed it, has to wait for cat. Every single word is just another link in a chain, and you can't forge the next link until the previous one is set in place.
Now, this is a really critical distinction. The actual calculations for a single word, a single step, that part might be incredibly fast. That's not the bottleneck here. The problem is the structure that connects the steps. The math itself is trapped in this sequential chain. This isn't a slow hardware problem, it's a slow architectural problem.
And the consequences of this are pretty clear. The longer the sentence, the longer the chain. And the longer the chain, the more all that waiting just accumulates. This is exactly why processing long documents like paragraphs, articles, entire books was so ridiculously expensive for these earlier models. The cost of waiting just became way too high.
But what if you could just break the chain entirely? This is where a new architecture comes in, and it changes absolutely everything. Let's call it System B, the attention grid. This is the core idea that powers the transformer.
The fundamental difference is right here on the screen. The chain processes one word at a time. The grid, on the other hand, is built from the ground up to process all words at once. It's a huge shift from thinking of a sentence as a line to thinking of it as a surface, from a sequence to a whole network.
With this system, the entire sentence is just presented to the model all at the same time. No word waits for another. Cat doesn't have to wait for thee. Ran doesn't have to wait for chased. That entire, slow, painful dependency chain, it's just gone.
Okay, now this is a really crucial point. The mechanism that makes all this possible is called self-attention, and it removes long temporal dependencies. It doesn't mean there are no dependencies at all. Of course not. The relationships between words still have to be calculated. The revolutionary difference is how they're calculated, all at once, in parallel, instead of one after the other. So how on earth does it do this? Well, on a conceptual level, every single word in the sentence gets to simultaneously ask every other word 3 basic questions. There's a query, like, hey, I'm the word ran, who should I be paying attention to? There's a key, well, I'm the word cat, and here's what I'm about. And then a value. Okay, ran, since you're looking for a subject, here's my info. This happens for every word, all at the same time, creating this incredibly rich grid of relationships without anyone having to wait in line.
So, let's put these two systems side by side. This is where you can really see the breakthrough. This is where the whole story really comes together.
On the left, you've got the chain. Slow, methodical, completely bound by time. And on the right, you have the grid. Every connection firing at once. The breakthrough wasn't some smarter algorithm, not in the way we usually think about it. The fundamental logic didn't really change.
Instead, we changed the shape of the computation. That's it. We took a problem that was structured like a long single-file line, and we just reshaped it into a grid. This one move was the key that unlocked everything that came next.
And why did that one change matter so much? Because we live in a world of parallel hardware.
By just removing that long chain of waiting, the transformer architecture allowed us to finally use the massively parallel computers we already had and use them efficiently. The math could now be spread out across thousands of cores all at the same time.
I mean, think about that for a second. The powerful parallel processors, they were already there. They were basically just sitting around waiting for a problem that was shaped correctly for them to solve. This was an architectural innovation, not a hardware one. The software blueprint finally caught up to the silicon.
So let's just recap the logic one last time. Old systems were built on these long dependency chains. Those chains forced the math to happen sequentially, to wait. And that waiting was a fundamental blocker to scaling up on parallel hardware. But then the attention mechanism came along and broke that chain, removing the long waits. And with the waiting finally gone, our parallel hardware could be unleashed to its full potential.
So, if you take just one thing away from this explainer, let it be this. Transformers didn't win because they suddenly made computers smarter. They won because they stopped making the math wait.
Of course, solving one bottleneck often just reveals the next one. Getting rid of the waiting problem was a monumental step, for sure, but it wasn't the end of the story. In our next explainer, we're going to look at why memory bandwidth, not computational speed, became the new great challenge to overcome. I'll see you then.